Okay, so good evening again. I am Shreya and the TA for this course, and today I'll be discussing some problems based on week 7 lectures. Okay, so before going into the problems, I would like to discuss why we go for polynomial regression. So, as I have written, the scatter plot, like for linear regression, what example we gave? Suppose this was a scatter plot, this is my x, this is my y. So if we observe something like this, so that a linear a line can be fit, then we go for a linear y equal to mx plus c fit. Okay, and in higher dimensions we go for a multiple linear regression. But here the thing is, when the scatter plot indicates scatter plot in case of a two variable scenario only, otherwise it's not possible to visualize. So if the response is something like this, let's say okay, so this one is a non-linear curve. This could be a polynomial, or if it, let's say if it's a parabola or something. So this is these are situations where we would go for polynomial regression. Okay, and what do we mean by the order of the polynomial? Suppose we have something like this one, and what is the order of the polynomial?
4.
Yes, so this one, the highest term. Okay, this is 4. But usually we would prefer models with order less than equal to 2 or 3 max, because we don't want to make our models to be very complicated. Okay, first we would go for some kind of transformation if it can be linearized or so. If not, then we would go for a polynomial fitting, and we would prefer models with order of the polynomial less than equal to 2 or 3. Okay, and the model building strategy is forward selection. So do you remember what was forward selection?
We are 1 by 1 degree.
Can you explain a little more?
Suppose in first case we take beta 0 plus beta 1 x. And if beta 1 is significant, then we add beta to x square.
And
So on.
And how do we stop?
जिस पैरामीटर पे इंसिग्निफिकेंट मिलेगा वहाँ पे हम एंड कर देंगे प्रोग्राम, मतलब कि ये प्रोसेस एंड कर देंगे.
Okay, means if this one is insignificant, then
यस, देन b3x³
यहाँ पे
पे
end
एंड हो
करेंगे.
जाएगा.
हाँ.
यस.
Yes. So we would proceed to test sequentially each of these parameters, and wherever we find that the subsequent one is insignificant, we'll stop at the previous one. This is how we would build our models. So, and another concept also was discussed, that is ill conditioning. So do you remember?
यस मैम.
Okay, can you explain?
मैम इफ जो हमारा मतलब कि वेरिएबल होगा उसकी वैल्यू मतलब कि बहुत स्मॉल होगी, तब उसका x² मतलब कि वो लीनियर मल्टीपल में हो जाएगा, मतलब क्वाइट सिमिलर टू लीनियर मल्टीपल. सपोज x है तो x² का टर्म पॉइंट समथिंग इनटू x हो जाएगा, तो मतलब कि वो लीनियरली मतलब कि नियर टू सिंगुलर हो जाएगा, मतलब कि उसका मैट्रिक्स.
हाँ.
वो इल कंडीशनिंग बोलते हैं उसको.
Yes. So if we have uh, x square, x cube, if x is very small, then these columns would become nearly linearly dependent. Okay, and then it would give rise to the problems of multicollinearity. So that is why to remove what is the strategy to remove or partially control for ill conditioning?
Centering.
Yes. And how do we do that?
x माइनस एक्स बार की जो प्रोसेस होती है वैसे.
हाँ. So this one would, this column, for initially we had 1x square x cube, let's say. Okay, now we have 1 x minus x bar, and this would be
x माइनस एक्स बार स्क्वायर.
exactly not x square minus x square bar whole square, not that. Okay, x minus
Yes.
x bar square. And x minus x bar cube. And after centering, we would go for forward selection one by one, and then we would fit in practical scenarios. That is how we fit the model. Now, while we are adding on terms one after the other, if we go by the natural procedure, we face the problem of recomputing again and again. So this was also discussed. Let's say I'll say it once again as well. So suppose we have in the first step beta naught plus beta 1 x. So here we are getting some estimate beta naught, beta 1. Then when we are adding beta 1 plus beta 1 x plus beta 2 x square, then these estimates beta double hat, beta 1 double hat, beta 2 double hat, these are not equal. So every time we go on, keep on adding terms, we need to recompute the coefficients. So this becomes computationally challenging. And that is why if the x columns, if the x are equally spaced, or otherwise, we know the formula for this one, then we could go for fitting orthogonal polynomials. Okay, even if it is not equally spaced, it can be done, but we just we are not aware, we are not aware of the ready-made formula as we are when x's are equally spaced. Okay, so please, if anybody has not followed the lectures, please go ahead and look at the lectures, and you would find how to fit orthogonal polynomials. And the advantage of fitting orthogonal polynomials is we need not recompute, and we can add and test significance of higher order terms easily. Okay, and then after that we talked about splines, fitting polynomial splines, which are nothing but piecewise polynomials of order k. Order k means the last term is x to the power k, beta k x to the power k. This is the last term of one piece. Okay, so let's say we have something like this here, then something like this here, and then something like this here. So this one can be fitted by a cube, let's say a quadratic fit. This could be a linear fit. Here the k would be 1, here k could be 2, here the k could be something 3. Okay, so these 3 are splines. And the joining points, that is this one and this one, these are nothing but knots. So while fitting, we have to, the points that we should keep in mind is that we should have as few knots as possible, and in each of these segments there should be at least 4 to 5 data points, because with 3 data points fitting a line in a single piece, it doesn't make sense. So at least 4 or 5 data points in a single spline, and as few knots as possible. Okay, and also we learned about polynomial models in 2 or more variables. For example, if we have something like okay, so this is a polynomial. I am saying it could also be a linear term, so I'll just rewrite whatever I wrote here. So we could have something like beta naught plus beta 1x plus beta 2x square plus beta 3 x2 plus beta 4 x2 square plus beta 5 x1 x2 plus epsilon. Okay, so in x1 it's a polynomial of order 2, in x2 also it's a polynomial of order 2, and we also have x1 x2. These are the, and the coefficient corresponding to these cross product terms are the interaction effects, and we have seen how we can calculate these and how to test for these things. Okay, this was all that was discussed in week 11 lectures. So any specific doubt from the lectures, anybody?
No, ma'am.
Okay, so then I'll proceed to the problems. The problems are fairly simple, just it involves a lot of computation, and don't worry, during the exams you won't be given such extensive problems, but the concepts are fairly simple. So let's start. So look at this data. This presents the strength Y of kraft paper and the percentage of hardwood in the batch of pulp from which paper was produced. And the scatter plot of the data suggests a quadratic model. So if you look carefully, you will see a trend in this data. On careful observation you can see as x increases, y is also increasing, but the rate of increase of y is more. I mean, here the rate is fairly 0.5 to 1, Okay, and here you see it's 6, then 11, then 10, then it is growing abruptly, and then again it's reducing. So if you plot the scatter plot, you will see that it is not really a straight line fit, it's kind of a curve fit. Okay, so the scatter plot also suggests that it is a quadratic model. So I'll just try to draw the scatter plot and show. 1 second. So this is how the scatter plot is looking for this data. It suggests that it's a something like this. Okay, so from here they are saying to remove non-essential ill conditioning fit this model. And now why they are saying ill conditioning, that will also become evident. So if you look carefully here I have plotted, I mean I have tabulated the values of x square, x minus x bar, and x minus x bar whole square. So the correlation coefficient between these two comes out as 0.97, which means these are more or less linearly related, highly linearly related. But once this centering is done, then that correlation coefficient reduces to 0.3. Okay, so this is how a highly, as I was saying here, the difference between the x's is very small, 0.5 to 1. Okay, and while squaring also, the x squares are fairly close enough, and the correlation coefficient, it relates that it says that there exists a highly linear relationship between x and x square. But once we center the data, that linear relationship is to some extent broken down. Okay, so this is one such example where we can see that centering is really helping. Now, to fit the model, what do you think? Should we go for orthogonal polynomial approach, or should we go with the normal approach? Anybody?
Orthogonal approach.
Okay, so if we go for the orthogonal approach, what do you think should be what do you think should be the orthogonal polynomial?
Both polynomial are mutually orthogonal. All polynomial.
All polynomial. So how many polynomials do you think we should need?
3 polynomial.
Okay. So you are saying we need 3 polynomials. So we can rewrite this thing as y equal to alpha naught p naught x plus alpha 1 p1 x plus alpha 2 p2 x plus epsilon. This is what you are saying?
Yes, ma'am.
Okay. Now p naught x would be
Constant 1.
1. p1 x would be
X minus x bar upon d.
okay.
into lambda 1.
Okay, so what will be D?
D is a level of observation number, मतलब कि suppose 1 2 3 है तो 1 आएगा D.
Okay, and lambda 1?
Lambda 1 is a coefficient for transferring in integer. Suppose x minus x bar upon D is a non-integer term,
Hmm.
then we can convert in integer.
No. Okay, so this one you are saying D is the observation number,
Yes.
right?
नहीं
So
नहीं observation, yeah, observation number नहीं मैम. Suppose 1 2 3 is constantly increasing, then level between two observation is 1 only.
okay, so here basically D is the difference between xi and xi minus 1. This difference only you are saying, no? Hello?
Yes ma'am, don't know exactly.
Okay, so far in the questions that we was done in the class, we have seen that the x's are increasing uniformly. So in that case, D was the difference between any two subsequent x observations. Like
Okay.
if this was 1, 1.5, 2, 2.5, then we could have written D equal to 0.5. Okay.
Okay ma'am.
So that we the point of choosing, we have to choose lambda in such a way such that this term becomes an uh, it becomes an integer, right?
Yes ma'am.
Okay, so here from by apparently looking at the model, we we are facing a challenge of not able to determine what this D is and what the lambda is, right? So when we are facing such dilemma, it is better to and also when the x's are not equally spaced, because all problems that we have done till now, x's are equally spaced. So when we are seeing that the x's are not equally spaced and we are not sure about what lambda 1 and d could be, then it is best to go to treat these things as a multiple linear regression model, because we would arrive at the same answers ultimately.
Okay ma'am.
Okay, so that is the reason we will take the other approach to solve this problem. So similarly, so once if we are able to identify lambda 1 and d, it's fine, we can go ahead with that. But if not, then we will go with the, we'll treat x minus x bar as some x1 and x minus x bar square as x2, and then this fitting the entire model would become equivalent to fitting y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. So this is a multiple linear regression in y, x1 and x2. Okay, so
Okay ma'am.
so once we have this thing, then it becomes fairly simple. We just need the the model matrix, that is the x matrix, x minus x bar. So here x bar was 7.26, we just computed x minus x bar and then we got x minus x bar whole square Okay, and once we got this, then beta is this thing, and beta hat is nothing but x transpose x inverse x transpose y. Okay,
Okay.
so here we just need to compute what comes as x transpose x inverse x transpose y, and then we would get three terms over here. I will just look at what comes. It is 45.295, 2.546 minus 0.635. Okay, so then we easily know that beta naught has this one 45.295, beta 1 hat is 2.546, and beta 2 hat is minus 0.635. So we have all the estimates. So beta 1, as I said, is 2.546, and beta 2 is minus 0.635. Okay, now I am just going to check, or if we are given something like this, where we can ascertain that d is 0.5 or d is constant, it's constantly increasing, there we can take the polynomial approach, orthogonal polynomial approach. So this we can write it equivalently as alpha naught plus alpha naught alpha 1 p naught x plus extremely sorry, alpha naught p naught x plus alpha 1 p1 x plus alpha 2 p2 x plus epsilon, where p naught x is 1, p1 x is lambda 1 x minus x bar by d, and p2 x is lambda 2 x minus x bar by d whole square minus n square minus 1 by 12. Okay,
Okay.
so now solving these with the we know that alpha naught hat is nothing but y bar, alpha 1 hat would be summation yi p1 xi by summation p1 square xi, and alpha 2 hat would be summation yi p2 xi by summation p2 xi square. So these things we know, but if we are asked to find out beta naught, then reporting alpha naught will be incorrect. Okay, so in such scenarios, what we need to do is this thing. So we have my pen is not working, just a second. Okay, so we had this one beta naught plus beta 1 x minus x bar plus beta 2 x minus x bar square. And we are writing it as alpha naught plus alpha 1. P1 was lambda 1 x minus x bar by d plus alpha 2 x minus x bar by d whole square minus n square minus 1 by 12. So this implies that y can be written as alpha naught plus alpha 1 lambda 1 by d x minus x bar plus alpha 2 by d square x minus x bar square minus n square minus 1 by 12. So again, by rearranging, we can write it as this thing plus alpha 1 lambda 1 by d x minus x bar plus lambda 2 by d square x minus x bar whole square. So once we have the alpha i's, we need to revert back. This one will be beta 2. Okay, this one will be beta 1, and this entire thing is beta naught. So once we have, okay, we should have an alpha 2. So once we have the hat values, I mean the estimates for alpha naught, alpha 1 and alpha 2, then we can, by calculating these modified versions, adding and by doing these adjustments, we would get beta naught hat, beta 1 hat and beta 2 hat. Is this clear?
Yes, ma'am.
Okay, please make sure, if you are using the orthogonal polynomials technique, then please make sure that you revert back to the original and bring it to this form so that you can report these coefficients. Okay, this is very important, otherwise you will get a incorrect thing. So here if you are given a polynomial regression, the forms, then it's good. If not, if it is equally spaced, then you have to use these forms. Okay, this was as discussed in class, and lambda you have to choose in such a way such that p1x and p2x become integers. Okay, so once we have the estimate values, then it is fairly simple. We have been asked to consider the data in problem 1, that is the one where it was not equally spaced, this one. Okay, I'll just do one thing. I'll copy this. So this one. Now here they are saying, consider the data. What is the MS regression for the model? So formula, do you remember? Okay, MS regression is nothing but SS regression by DF of regression. Okay, you agree with
Yes,
me?
ma'am.
Okay.
Yes, ma'am.
Now also we know total sum of squares is sum of squares due to regression plus sum of squares due to residuals, and our model was this one. Okay, so the total DF would be, and we have n observations, n equal to 19. So the total DF would be what? How much?
N minus 1.
N minus 1, that is 18. And this residual DF would be how much?
K minus 1, 2.
Residual.
Residual 16.
16. That is n minus number of unknown parameters. That is 16. And regression would be k minus 1.
2.
That is 2. So MS2, in order to find MS regression, we just need to find SS regression by df of regression. So do you remember SS regression? What was the formula? Okay, if you don't remember, it's fine, we'll just compute. SST minus SS regression. This one we know is nothing but y minus y bar prime y minus y bar. Okay, or summation, I'll write, this will be easier. This is nothing but sum of squares, total sum of squares is summation yi minus y bar whole square. Okay, and minus
SS residual.
SS residual. Yeah, 1 second, I wrote this incorrectly. Yeah, this is SS residual. So I remember SS residual more carefully, so I will use this approach frequently. So SS residual is nothing but y prime y minus beta hat transpose x prime y. Okay, and SS total is summation yi minus y bar whole square. So this thing comes out as 3416.885, and this thing, see, we have the beta hat values. No, beta naught was 45.295, 2.546 minus 0.635. So y prime y is nothing but summation yi square. So this one we know, this one we can compute. So this entire thing, SS residual, it comes out as 312.64. So MS regression is nothing but 3416.885 minus 312.64 divided by the df, that is 2. So this would finally come out to be 1552.123. Okay?
Okay, ma'am.
Okay. And this one, MS residual, is how much? So SS residuals we have calculated y prime y minus beta prime hat x prime y. So the main technique is, you don't have to remember all SS residual, SS regression and everything. One, you prioritize, you remember that, and just subtract it from the total sum of squares. So this is one easier technique. Instead of memorizing two formulas and getting confused, you pick one and you memorize one. Okay.
Yes.
So SS residual we got it 312.64, and MS residual is SS residual by residual df, that is nothing but 16. How we got? N minus 3 unknown parameters. So this would come out as 19.54. Okay, I hope this is clear. Again, the same kind of questions. Degrees of freedom of SS residual is 16. And then we have this question. Suppose we wish to test the hypothesis beta 1 equal to beta naught equal to 0 against H1, that H naught is not true. So we have this one, sorry, which is in essence something like this. And we have been asked to test whether beta 1 and beta 2 are 0 or not. So what would be the statistic for this one?
SS regression, मतलब कि MS regression upon MS residual.
MS regression upon MS residual, because this is a global test of significance of the regression line. Okay, so there, this was our test statistic. And so we have the MS regression value as 15,1552.123 by 19.54. This is coming out as 79.433. And what would be the F critical value? We should compare it with an F with df1 and df2 equal to
2,16.
Yes, 2,16. Okay, because here there are two restrictions and the full model had a df of 16, error df 16. And let's say the critical value at alpha percent 5% level of significance. So this is my critical point. So we'll reject H naught if and only if F observed is
Greater than
F2
critical.
16, F critical, exactly. So F critical is how much? Let us see. So df1 is 2 and df2 is 16. So 3.63. For alpha 0.05. Okay, so this is 3.63. And our observed statistics is way more than the critical point. So we'll reject H naught. Okay. Okay, and now let's focus on this one. So they are saying, can the second order term be deleted from the fitted equation? So which one is the second order term?
B2x minus x bar square.
This one. So if this has to be deleted from the fitted equation, then our H naught becomes testing beta 2 equal to 0. Okay. So in order to test this, we will use the extra sum of squares approach. Okay. So we are to test B2, that is beta 2 is 0 in the presence of beta 1. So the F statistic is nothing but SS residual from the restricted model minus SS residual unrestricted divided by number of restrictions and whole divided by MS residual from the unrestricted, which is also sometimes called full model. So we have information on this one, we know, this one also we know. So what we need to do, that we need to compute SS residuals from the restricted model. So how we are going to do that? The restricted model is nothing but this one, because beta, we have set beta to equal to 0, so we will not have. So this is the restricted model. So similarly, we would have the X matrix like this one, and without the third column we would have our model matrix. Then beta hat becomes X prime X inverse restricted X prime Y, and if we calculate, we'll get this as one second, I have it here with me. Okay, this was something like 34.184 and this one was 1.771. Okay, so SS residual from this restricted model is nothing but y prime y minus beta restricted x prime y. Let me write just x star, where x star is the model matrix for the restricted model. So if we do this calculation, then we would get it to be something like 2373.458. Okay, this is y prime y is nothing but the summation yi square, and we have beta, so beta prime x star prime, this one is x star, and y would give us this thing. So then it becomes fairly simple. We will just use the formula sum of squares residuals from restricted model minus sum of squares residuals from full model, and we should divide it by how much? What is my r here?
1.
Yes, r is 1 since we are testing only beta 2 equal to 0. 1. So this one by ms residual. So finally this is 23.734 minus 312.64 by 19.54. This is 105.47. And the critical value would be, what would be the degrees of freedom? Hello?
Yes, ma'am. 160.
It will be 1 and 18. 18 or 16?
16.
16. Why? because this ms residual is from the full model.
Full model.
Full model had 3 unknown parameters. So 19 minus 3 was 16. But the restricted model has a error df of 19 minus 2. Okay, that is 17. Okay, so this one is 16 because we'll consider denominator will always be with respect to the full model, and 0.05. So again we'll go back to the table. So df1, I mean this one, and then 4.49. So this is 4.49. So here also we will reject h naught, that beta 2 equal to 0, and so the conclusion is that the second order what was the question? Second order term cannot be dropped because it is highly significant in the presence of the first order term. Okay, so I am almost at the end of today's session. So yeah, this is only what I have for today's class. One thing I would like to say is that once you are getting the, if you are if you are going to fit an orthogonal model, just remember the basics and those kind of things, like the ss residual, it becomes y prime y minus alpha hat prime x prime y. Okay, and so alpha hat we had gotten from this alpha naught hat was y bar, alpha 1 was summation yi p1 xi by summation p1 xi square, and so on and so forth. But this main equations, they remain the same. So even if you don't remember the actual, like this would be something sst minus summation alpha j hat summation yi p j xi. So if in case you are unable to remember these formulas, you just remember the basic multiple linear regression formulas, and once you have the coefficient, the alpha values, you use that in the subsequent models, and you go back to the lectures and you see how it was how these formulas were derived. And if you are unable to remember so much of granularity, you just remember the basic formulas and try to derive it, or put the values there, substitute the values in those main equations, and then arrive at the final concluding answers. Okay, like if I have this variance of alpha hat would be nothing but sigma square x prime x inverse only. Now the x matrix is not the usual x matrix, it is p naught x1, I mean it will be 1 1 1 1, and then p1 x1 p2 x2 pn xn p1 1 second. So instead of the normal x matrix, in such scenarios where you are solving it via orthogonal polynomials, you would have the x's as this 1 1 1 1, then this one would be p1 x1 p1 x2 2 p1 xn, and this would be pk x1 for a kth order polynomial, pk xn, and once you do x prime x, you would end up with a diagonal matrix, that is summation p naught xi square summation p1 xi square summation pk xi square, and you just need to do x prime x inverse x prime y, and to get the alpha hat, and variance of alpha hat would be sigma square x prime x inverse. So this matrix, if you just do an inverse, and alpha j hat, if you are asked to find the variance of alpha j hat, it would be sigma square x prime x inverse the jth element of this matrix into sigma square. Okay, so the main thing that I want to convey is that you remember the main formulas. The other things is just modulation of the X matrix. Okay, and that is how you will arrive at the final answers. Okay.
Yes, ma'am.
Okay, so I'll stop my session now. Do you have any other questions from today's class or this week's lecture?
No, ma'am.
Okay, so thank you so much for joining, and we'll meet again next week with week 12 problems. Okay, thank you very much, and if you do have questions, use the discussion forum. Thank you.